we continue on here. Let's look at the concept here of power required. Trying to get into your head, if you got a 3,000 pound airplane, we need to develop roughly 3,000 pounds of lift. Part of that lift production comes from the forward speed of the aircraft and having the wing produce lift. Part of it comes from the angle of attack as well. But angle of attack produces more drag, which slows down the airplane. Of course, power overcomes drag. So this isn't a mathematical formula where you can plug numbers into it. It's more just a concept here that when I'm flying an airplane in level flight, the speed that I want to obtain with consideration for the drag factor in there, clean, or flaps down, landing gear down, right? That's one half of the equation. And the other half is, well, how much weight is there on the aircraft? So I need a certain amount of power based upon the weight of the aircraft. And what sort of vertical speed factor do I want to use? So we do remember that an airplane climbs because of excess power. That means excess power over that which is needed for level flight. So it boils down to how fast do you want to fly your airplane, and at what vertical rate do you want to fly your airplane? Then that gives you the concept of how much power that you actually need for level flight. So we're going to complete some power curves here. So that was a handout that was available online. So if you printed it or you're using a digital copy, you'll be able to fill these in. We're going to start with the power curve. And these are all, this will be the standard one, our baseline for level flight. With the concept that flying the aircraft, say a 3,000 pound airplane, I need to develop 3,000 pounds of lift. Based upon the engine and propeller that I have and the amount of power that I'm applying for my phase of flight, I have a certain amount of power that's available. Typically, this is going to be a fixed pitch propeller that we're talking about. And the propeller efficiency is part of the reason why we have this curve in the power available curve. And also part of the reason why it starts to dip as we get to the high speed portion on that curve. When we get to the high speed portion, the propeller efficiency drops off because typically the tips have reached a stall point. And they're starting to produce a little bit of drag now and not as much thrust. A 3,000 pound airplane, I need 3,000 pounds of lift. We can equate that to, I need a certain amount, based upon that little concept formula on the last slide, I need a certain amount of power just for level flight. And I can see that as I go faster, I need more power. But interestingly enough, as I go slower, I need more power. And if you're thinking this power required curve looks a lot like a drag curve, then you are thinking the right way with it. And where the two curves meet at the right side there, that's your fastest possible speed in level flight. And that's it. You just can't go any faster and maintain level flight. And the same thing on the far left side, where the two curves meet, that is your slowest possible flight speed before the aircraft would stall. Trying to fly it any slower, you're below stall speed. And you know where you go from there. Now looking at the distance between these curves. On the left side, the distance between curves is a little bit. And on the right side, the distance between the curves is a little bit. But as you progress towards the middle, the distance between those curves increases. And that's important to recognize that when I get to that greatest point between the curves, the greatest distance there, I have my maximum excess power. And remember, maximum excess power is used to climb the aircraft. So the point at which that occurs does happen to be my Vy speed. So my best rate of climb is going to occur there. To the left side of that point there, we have a bottoming out of the power required curve. This is a very special point. It's called the minimum power point, or minimum power speed. It's interesting that on either side of this, your power setting could result in a fast speed or in a slow speed. So one power setting here could result in this slow speed, or it could result in this faster speed. But minimum power speed, there's only one one power location for this speed. You set this power setting, you're only going to get this speed. That is going to divide this power curve into two regions. And when I look at the region to the right side, that's where I conduct my normal flight. And that is known as the front side of the power curve. You know you're on the front side of the power curve when you add power, you go faster. To the left side of the minimum power speed is my region for slow flight. Slow flight also goes by the backside of the power curve. You know you're on the backside of the power curve if you want to fly slower, you need more power. If you want to fly slower, you need more power. Now notice I did not say add power to fly slower. That's not it. If you want to fly slower, like put the landing gear down, you need more power. If you're adding drag into that mix there, you're going to need more power to overcome that drag that you introduced. All right, so that minimum power speed point typically is also the point where you get your best glide. That's your maximum lift to drag ratio. And just for comparisons, I'm throwing up there VX speed for you. We're not going to talk about how they determine VX speed, so I'm just throwing it up there for you. All right, so what happens if we were to increase our altitude? We're going to start with our basic baseline curves here. One thing we know is we go up in altitude, I have fewer air molecules to work with, so my power that's available has reduced. So not as much power is available anymore. I still got my 3,000-pound airplane. I still need about 3,000 pounds of lift to make it fly. In order to do that, I'm either going to use more engine power or greater angle of attack. Well, greater angle of attack results in more drag, so more engine power is needed. So hence the curve does move upward for power required. So higher altitude, because of less air molecules, I don't have as much power available anymore, and I need more power than the lower altitude just to maintain level flight. So the results of that mean I cannot fly the airplane as slow In other words, increased stall speeds. And I can't fly the airplane as fast in level flight. I'm just using more of the power to maintain level flight now. It also means that the distance between the curves has changed as well. So that the maximum excess power is now reduced. Your ability to climb at certain rates, they're now reduced. So one thing we notice as we go up in altitude, the VY speed decreases. And you can easily confirm that in your operating handbook in the performance section for climbing. Another interesting thing to note is VX speeds increase. And if you ever want to know how high you can fly an airplane, when VX and VY meet, you'll also be at the stall point of the aircraft. And this is as high as you can fly the aircraft. All right, so that's one aspect if we change altitude. But what if we change the weight of the aircraft? So we're at that lower altitude. Here's our baseline curves. We change the weight. I still have the same amount of power that's available to the aircraft. But the fact that I'm now at a higher weight, say 4,000 pounds, I need roughly 4,000 pounds of lift. So either increased angle of attack or increased speed. Either way, I'm going to have more power that's required just to maintain level flight. So again, you can see that our maximum speed and our stall speeds have now changed. Can't fly as fast, and stall speed is higher. Distance between the two curves is also reduced as well. Again, we're using more power just to maintain level flight here. All right, fun stuff. Gotta love aerodynamics. I want to see if I can help you understand this with this video of this aerobatic airplane coming in to the field here. Go full screen with this. As this airplane comes in, it's slowing down, and you can begin to see the angle of attack increase on the aircraft. Just pause it for a second. You know, I'm got to keep in mind my engine developing that thrust. Some of it's acting horizontally, and I have airspeed. Some of it's acting vertically, and is helping in addition to the lift from the wing. So as we're slowing down, we're losing wing lift, but replacing it with the vertical portion of the engine. Okay. It'll become much more apparent here in just a moment. You can see the angle of attack's increasing. And this is a special airplane in that it is capable of effectively pointing the nose straight up and obtaining vertical flight. So you can obviously see that the wing is producing zero lift at this point. Everything's dependent upon the engine. You want to go up, add power. You want to go down, reduce power. We're just trying to emphasize that the relationship between angle of attack, wing lift, and the engine power, they go together. So you really got to stop thinking about this one control controls altitude or this one control controls airspeed. They're both related to each other. We do a quick touch and go here. Now as we start changing the angle of attack to its less than 90 degree, some of that engine power is now converted to horizontal power. And we get airspeed again, airflow over the wings. Pretty amazing pilot, wasn't it? Yeah. It was a radio-controlled airplane, by the way, if you were wondering. But it looks so real, didn't it?